Let's consider ratio control. An overview of what we'll look at is ratio control, then relation control, which is different than ratio control, and then the concept of reverse versus direct action. Ratio control is something pretty simple. You probably do it every day when you take a shower. You want to control the ratio of hot to cold water so that you end up with a nice, comfortable shower. An industrial example might be paint, where you're mixing a base with a pigment. And if we have a human operator here controlling the flow rate of both the base and the pigment, then somehow they'll have to decide exactly how to set these two. And really it's not the overall flow rate they care about as much as that the color comes out right. So maybe there's a flow transmitter from each of the two streams that you want a certain ratio of, and so there's a calculation Fy that is one divided by the other, and then a ratio indication Ri that the human being can look at and adjust both valves as necessary so that the paint comes out with a proper ratio. Now, an easier way to do this might be to have some sort of mechanical linkage between the two valves so that one is turned in proportion to the other. Probably not 1-to-1, but something that could be set for whatever ratio we wish. That way the human being doesn't have to work so hard. They can just turn one of the valves, and the ratio should be automatically set so that we end up producing paint that is of the appropriate quality. This is something that's actually commonly used in simple heating control systems where you have an actuator that turns a linkage or pushes a linkage in order to change an air damper for a furnace. Now when you let more air into a furnace you need more fuel, or vice versa. When you close the damper down a little bit you need less fuel so that you get proper complete combustion of the fuel and it's efficient and clean. So you can see a cam here also mounted on the link or on the shaft from the actuator that then pushes down a linkage and changes a setting on the fuel gas valve. And the idea here is that once adjusted properly, the air is metered out, or the fuel is metered out to meet the air and match the air and have the right flow rate. Now, even better than having the human being in our paint production line would be to have a controller that measures the temperature of both the pigment and the base. And if you want a 1-to-1 ratio, just make sure that the flow in each is the same. And so the process variable is the flow of the pigment, the set point is the flow rate of the base, and then we can simply adjust our production rate by controlling the valve that controls the base flow. And then the flow indicating controller, its job is to adjust the valve that controls pigment so that there's a 1-to-1 ratio of pigment to base. This may not be the best idea. Most of the time in paint what you really want is for the pigment to be less than the base. Most of the time the base is just a white paint base and you add a minority of pigment to it to affect its color. But in a 1-to-1 control, just as we consider here, there's the so-called wild variable. Now that's the base paint flow rate. So that's the thing that we have to monitor or measure in order to adjust the so-called captive variable, in this case the pigment flow, to some ratio, in this case 1-to-1. Now as I said, for paint production, a 1-to-1 ratio is probably not ideal. So instead what could be done is to take the flow rate of the base and then either multiply or divide it with some constant K in a a math relay, if you will, an Fy, so that the set point is scaled. So that, say, we want a 10-to-1 ratio, so we want 10 parts base, 1 part pigment. Well, then what we would want to do is take the base flow rate, divide it by 10, in other words, multiply it by 0.1, and let that be our set point for the pigment flow rate, whatever 0.1 is times the base flow rate. And then that would allow the flow indicating controller to control the pigment to some ratio of the base automatically. So this would be a multiplication or division, and it would be proper ratio control, not just a simple 1-to-1 ratio control. Here's another industrial example where steam and methane are reacted together over a catalyst in a furnace. Because it's an endothermic reaction, you have to put energy in to produce the hydrogen gas and the carbon dioxide. But the two are put into a furnace in order to make this reaction happen. And hopefully the products coming out are hydrogen and carbon dioxide. Now you'll notice that The methane flow at the bottom is being measured by a flow transmitter, and you'll note the square root sign next to it. That's because the flow transmitter probably uses a pressure drop in order to infer the flow rate, and it turns out that pressure drop and flow rate are related through a square root operation, but that's a fluid's flow idea and result. Anyway, so the flow rate of the methane is sent out to flow controller FC that controls the methane flow rate, basically the production rate. So we can set a set point for whatever methane flow rate we want. Notice that the actual measurement of the methane flow rate, though, also wraps around to the top to FY, which is a ratio device or mathematical device that multiplies the methane flow rate by some constant K in order to choose or to compute a set point for the steam flow, which is controlled by the upper FC on the steam line, with the flow transmitter for the steam line as well to measure the actual flow and change the valve to get some ratio of the methane flow. If you look at the stoichiometric setup in the chemical equation, you can figure out what the ratio theoretically would need to be. Now, in reality, there may be impurities in the methane stream. It's difficult to separate chemicals out. It costs energy. That's what thermodynamics tells us. And so it's entirely possible that a methane stream would also include some ethane, and the ethane could be broken down in the catalyst as well and make some hydrogen. And so the actual ratio necessary would depend on how pure the methane stream is. Maybe it's pure, maybe it's not very pure. Maybe there's even some propane in there. And so if we can analyze the gases coming out with the analytic tool, the transmitter there, AT, then we could use AIC, an indicating controller, to affect the proportionality rate, K, so that we can adjust the proportion of steam. Because if you think about it, if you don't put enough steam in, what will happen is the hydrocarbons will coke on the inside of the furnace, and it'll eventually foul the catalyst, and the catalyst won't work like it needs to. Often you can burn it off, but that's wasted production time and wasted effort. On the other hand, if you just put way too much steam in, then that represents lost energy. It's an inefficient process. And it's not a bad thing to run with a little bit of extra steam in a case like this, because you'd rather not have the furnace coke where you have to shut down the process and clean it out. But you don't want just a ridiculous amount of extra steam. And so analyzing the stat gases, or well, I guess it wouldn't be stat gases, but the production gases coming out, and setting a new ratio, K, for the flow rate of steam versus the flow rate of methane would be a wise choice in this case. Relation control is not ratio control. Ratio control is either multiplying or dividing one signal in order to determine what another flow, for example, should be. This is an example where we have a superheating boiler. Basically what happens is the feed water enters the boiler, and you see it go through the economizer first, where any exhaust gases help to preheat the water. And this is something that would be common in a coal-fired power plant or even a gas-fired power plant, where the water goes into a setup where mud can be withdrawn off the bottom, because often the water that comes in is not perfectly clean. And a principle of thermodynamics is that when you boil off water, the water that comes off in the vapor phase and the water that remains in the liquid phase are at the same temperature. And so the saturated steam coming off the top steam drum, its temperature is measured by temperature transmitter TT, and then that information is set or is sent up to TY. And the idea is that with superheat, what you want to do is you want to take saturated steam. The problem with saturated steam is if it cools down at all, some of it will liquefy out, and often that's not acceptable. You want to make absolutely sure that the steam does not liquefy, that it doesn't condense at all. And you need to superheat it. In other words, add some more thermal energy to it so that its temperature goes well above, the saturation point. Not necessarily just ridiculously above. Often what you want is a certain amount, degrees of superheat, say 50 or 100 degrees of superheat, as an example. And so the superheat set point is how much higher the temperature needs to be after the superheat section there at the end, those black pipes. And the way you control superheat is difficult to control, but the way you do it is you actually superheat the steam beyond what's needed. You make sure the flame is set up and the burning rate is set up so that You can superheat the steam well beyond what you need, but you just mix some feed water back in. So the temperature indicating controller, what it's doing is taking a desired temperature that is above the current measured saturated temperature and trying to add enough water in so that, liquid water, so that the superheated steam that comes out at the very end is not too far superheated. So we back it up a little bit. So you see two temperature transmitters. The one on the right is measuring the superheated steam coming out. The one on the left is measuring the saturated steam. And the goal of the controller is to make sure that the superheated steam coming out is only so many degrees above the saturation temperature. So this is an addition or subtraction type of device, the TY element. And what it does is it simply adds a certain amount to the temperature as the set point for the temperature indicating controller. And this is relation control, not ratio. Ratio suggests that you're multiplying or dividing. This is addition or subtraction, could be. Now, reverse versus direct action is an important concept. It has to do with whether gains are positive or negative. What's shown here is two cross sections of two different valves. They're both control valves. And the way they work, in the upper actuator, you can introduce air either into the bottom on the left-hand side of the diaphragm and push it up, which pulls the stem up, which pulls the stopper there and the valve at the bottom up and allows more flow through. Or in the right-hand side, you notice the air can be put in from the top and push the diaphragm down, which pushes the stem into the valve body, choking off flow. Now, the one on the left requires air to open. So if there was no air, if air failed, the valve would fail in the closed position because the spring would push the valve stem down into the valve body, which would close off the flow. So this is an air to open, a fail closed valve. On the other hand, the right-hand side photo is one, or illustration, is air to close. So you've got to push air into it to block the flow off. So this is a fail open valve. Now let's think about overall whether these are reverse or direct acting things. Your gas pedal's direct acting, for example. An increase in pedal position increases your car's speed. So an increase in the control variable increases the process variable. Is that what happens here? The valve on the left, if we put air into it, we're going to put it in under the diaphragm. That's going to push the diaphragm up against the spring and increase the flow rate. So an increase in air pressure actually increases the fluid flow through the valve body. I would call this a direct acting system. On the right hand side, that valve, we're putting air in from the top, which pushes the diaphragm down, choking off flow. So increasing air pressure decreases the fluid flow through the valve body, and that would be what I would term a reverse action. On the other hand, the valve body may be made differently, such that on the left-hand side, when we put air in beneath the diaphragm, it pulls up, and that actually pulls the stopper into the valve body and decreases flow. So in that case, what happens is an increase in air signal decreases the flow rate. So this is a reverse action, whereas overall the valve on the right-hand side, when we put air into the top, what that does is that moves the plug out of the way and increases the flow rate. Now, if we talk about just the valve body itself, then both of these are reverse acting gates, because as you push the stem down into the valve body, the flow rate increases. So a negative movement, if you will, increases the flow rate in both cases. Okay, so the valve bodies themselves are both reverse acting, but depending on the actuator added to the valve, the overall system can be reverse or direct acting. So going back to the example of the gas pedal in your car, I said pushing the gas pedal down increases your car speed, and that's a direct action. What if you're measuring it opposite? What if you're measuring position as positive coming up, right, releasing the pedal, and negative going down? Then an increase in the negative direction increases the car speed, so that's a reverse action. So a lot of this depends on which way you call positive and negative, but generally when we talk about reverse versus direct action, what we really mean is If I increase the control variable coming out of the controller, does that increase or decrease the process variable? If an increase in the control variable increases the process variable, that's direct acting or a positive gain. On the other hand, if I increase the control variable and it decreases the process variable, then that's reverse action or a negative gain. So we talked about ratio control, relation control, and reverse versus direct action.